Okay. Hello everybody. We start our lecture. Not so many students are here, but nevertheless there are. So next section, I think it's section 5, if I'm not mistaken. I'm not sure in numbering. First was about topology. Second, limit of sequences in Rn. Third, limit of functions. Fourth, continuity, right? So fifth, yeah. Section 5. Geometry of curves. In Rn. We had a definition of curve. Let me recall that a curve is the image of a continuous map from an interval to Rn. So if n equals to 2 or 3, better n equals to 3, the best model, then we can think about a curve as a trajectory of a movement. So a point moves and r of t indicates position of our point at the moment t in the space, right? If n equals to 3. But of course we can consider more general situation, as we'll do now. Okay, now a series of definitions related to curves. So simple curve is a curve without self-intersections. What it means rigorously, i.e., if r of t1 equals to r of t2, then either t1 not equals to t2 or t1 and t2 coincide with the initial and the end points. So if we think about t as a time, then r of a is an initial point of curve, r of b is a terminal point. So simple curve is a curve without self-intersections. Next definition, closed curve is a curve with r of a equals to r of b. So it means initial and terminal points are the same. So we start from a point and we return to that point. That is closed curve. And one more definition, a simple closed curve is called Jordan curve. It's called a Jordan curve. A Jordan curve. And Why Jordan? Because there is a theorem which seems to be very natural and, I would say, obvious from geometrical point of view. So in R2, if we have simple closed curve, right? What it means? We have a curve with same initial point and terminal point without self-intersection. Then it seems obvious. Then this curve splits the plane into two domains, right? And that is called Jordan theorem. And this is a theorem which I cannot prove to you because I haven't enough tools to do it, because there is no elementary proof of this theorem. This is very complicated assertion, although it seems absolutely obvious, right? Okay. That is why it's called Jordan, because Jordan proved it rigorously. So, next definition. Now we'll talk more about vector functions. So, a vector function R of t is called differentiable at t naught if R is defined in a neighborhood of t naught and there exists finite limit as delta t tends to 0, R of t naught plus delta t minus R of t naught divided by delta t. And this limit is denoted by R prime at t naught. So everything like for usual functions of one variable. And how to understand this ratio? We have a vector, and here we have a number, right? So it means we multiply vector by a number 1 over delta t. That is how to understand this ratio of vector divided by number. And proposition 1. Proposition 1 R is differentiable at t naught if and only if each coordinate function of R is differentiable at t naught. So, proof. So we have R of t is a vector function, so x1 of t, so on xn of t are coordinates, right? And then we know that limit of a vector function exists, there was a lemma in section 3 that a limit of vector function exists, this limit exists, if and only if there exists limits as delta t tends to 0 for each of coordinates xi t naught plus delta t minus xi of t naught over delta t I from 1 up to n. Rigorously speaking, this lemma was given for limits of sequences, but of course then we can extend it to limits of functions using Heine definition. So I didn't distinguish in fact between differentiability and the existence of derivative, that is vector derivative of vector function, right? That is vector derivative of vector function. And of course also we can prove another proposition to R is differentiable at t naught if and only if we can represent the increment, and the increment that is in fact change of position. So now if we can represent it as the following, so let's say delta t times vector A plus vector O of delta t as delta t tends to 0, where A is a vector and vector O is a vector which consists of several functions, and each of them is little o of delta t. So this is vector little o. Vector little o. Once again, this proposition is immediate if we use proposition 1, and then we apply definition of differentiability and the equivalence between differentiability and the existence of derivative for a function of one variable. So if we recall, so proof, we use proposition 1, and we can write every increment of every function xi as delta t, okay, I'll write ai times delta t plus oi of delta t as delta t tends to 0 and I from 1 to n, and that is precisely what was in our assertion. Okay, so also a lemma, or maybe also proposition 3. If R is differentiable, at t naught, then R is continuous. At t naught. Why? Look at proposition 2. So if it is differentiable, we can write like that. And then what happens if delta t tends to 0? The right hand side tends to 0. Hence, the left hand side tends to 0 as well. And what it means? Left hand side tends to 0. It means limit as delta t tends to 0, R of t naught plus delta t equals to R of t naught. And that is precisely definition of continuity. If we denote t naught plus delta t as t, so t tends to t naught. Okay. Next, proposition 4. Proposition 4. Rules of differentiation of vector functions. So, which letters I used? Okay, A and B. Suppose vector functions suppose that vector functions a, b are differentiable at t naught, and phi is differentiable at t naught. Then first, the sum and difference are differentiable at t naught, and also derivative is equal to the sum or difference of derivatives. Second, product of phi times a is differentiable at t naught, and phi times a prime at t naught equals to phi prime at t naught, a at t naught plus phi at t naught times a prime at t naught. Third, scalar product a times b is differentiable at t naught, and its derivative equals to scalar product of derivative at t naught times b at t naught plus a at t naught times b prime at t naught. Fourth, vector product for n equals to 3, vector product a, b is differentiable at t0, and derivative can be computed similarly. So it is called also Leibniz rule, right? So a prime at t0 times b at t0 plus a times b prime. So proof. Okay. How to prove it? The easiest way. The easiest way, of course, is to use presentations in terms of coordinates, right? So, for example, okay, first is obvious by coordinates, right? If we use by coordinates. Second, and others just by looking at coordinates. So, for example, phi times, let's say, x1, so on, xn prime at t0. So what it means? It means we differentiate vector, this vector. We multiply by scalar phi, right? And we know derivative of a vector function consists of derivatives for each component by proposition 1. Phi xn prime at t0. And lastly, we apply differentiation of product, right? What is it? That means I should write phi prime at t0 times x1 at t0 plus phi at t0 times x1 prime at t0 and so on, phi prime at t0 times xn at t0 plus phi at t0 times xn prime at t0. So what is written here is the sum of two vectors. One vector with those components, first terms of the sums, and second vector with second terms of the sums. What is it? Little o is representing the same notation that when we set the limit of that is tending to 0. Yeah, here little o is the same as for one variable, right? We know what is little o. That is a function which tends to 0 after division by delta t. You divide by delta t and it still tends to 0. Remember, little o. Yeah? And here just vector, which consists of such little o's. Okay. Yeah. Now, so we have a sum of vectors. Then look, for the first vector, we have common scalar multiplier phi prime. So I can write first phi prime at t0 times vector with coordinates xn at t0, so on, xn at t0. And for the second vector, we have common multiplier phi of t0. And vector consists of derivatives. And that is precisely what is here. Because we multiply firstly phi prime times vector A, and secondly phi at A prime. And analogously, we consider all other rules. So, okay, let me do it for scalar product. So second, for scalar product. So A, B prime, we need to differentiate the sum of components. Okay, if A of t as before, like that, and let B of t be y1 of t, so on, yn of t, then here we should differentiate the product of for t equals to t naught, and we differentiate sum derivative of sum equals to sum of derivatives, right? And then we differentiate each of terms as a product, right? So we obtain sum I from 1 to n xi prime of t times yi t naught plus xi at t naught times yi prime at t naught. And then we separate once again as a sum of two summations, and like that, xi prime yi plus xi times yi prime, and these are scalar product A prime times B plus here A times B prime, and we are done. For the third, we need to remember what is vector product. So I need to recall what is AB. That is a vector which consists of which components? So let me recall. What is a vector product? AB. That is determinant I, j, k, vectors, basic vectors, right? I, j, k, and then we should write coordinates. So x1, x2, x3, y1, y2, y3. So we have x2, y3 minus x3, y2. First component, second component will be x3, y1 minus x1, y3. And third component, x1, y2 minus x2, y1. We should differentiate it at t naught. Vector derivative consists of derivatives, so and here the expression will be essentially ln, because each product gives two terms, right? Differentiate first, multiply second, and so on. So x2 prime y3. I'll indicate t naught at the very end, otherwise it's very huge. Plus x2 y3 prime minus x3 prime y2 minus x3 y2 prime, that is the first component, x3 prime y1 plus x3 y1 prime minus x1 prime y3 minus x1 y3 prime, that is second component, and the last third component, x1 prime y2 plus x1 y2 prime minus x2 prime y1 minus x2 y1 prime at t naught. And now look, if we consider only derivatives of x's, right? So look at underlined components. What is it? First component, that one, right? x2 prime y3 minus x3 prime y2. It's like that one, right? But with primes over x's. Similarly for second component, also like here, but primes over x's. And for the third component is same. So what we have precisely this determinant, but with primes over x's. It gives a prime times b. So a prime at t naught times b at t naught, that is what is underlined, right? And sorry, comma here, plus, and also components which are not underlined, what they are. Similarly, you see, it's the same determinant, but primes are over y's now. So we have vector product. So here a prime, I forget, sorry. A at t naught times b prime at t naught. That is. So everything is proved now, right? Okay. So you can think that everything is like for functions of one variable, right? Just component wise. But there are things which are different. So, for example, mean value theorems. So, Remark the Lagrange mean value theorem cannot be generalized to Rn. Example. Consider n equals to 2 and such a vector function. Cosine t, sine t, let's say t belongs to 0 to pi. If you think a little bit, what is it? So that is x, that is y, right? X squared plus y squared equals to 1, right? So we have precisely trajectory, circular trajectory, right? So we start t equals to 0. We start at 1 on the real axis, and we move counterclockwise along the unit cell. That is our curve. That is our curve, right? Now, look, if we try to, for example, just try to use mean value theorem. So if we apply just for the difference of r of 2 pi, then, okay, psi times 2 pi minus 0, right? That is what we could expect from Lagrange mean value theorem, right? Because, look, for usual functions, right, if these are not vectors, that is certainly true. For arbitrary differentiable function, right, over 0 to pi, you can find xi between 0 and 2 pi such that this equality holds. Lagrange mean value theorem for usual functions, right? Now we are looking for a vector function. Then what is it? That is 0, right? Because points are coincide, so difference of vectors. R vectors are those vectors. Same vector, right? R of 2 pi and R of 0 are the same vector, so the difference is 0 vector, right? But R of t is never 0, right? It goes around 0, but it is never 0, you see. So left-hand side is 0 vector, right-hand side is 2 pi times non-zero vector. So equality is not possible. Equality is not possible. So Lagrange mean value theorem cannot be generalized as directly, I would say. Nevertheless, we can formulate Lagrange mean value theorem for vector functions. Theorem 1, Lagrange mean value theorem for vector functions. If R is differentiable on AB and continues on AB, then there exists psi in AB such that the length of difference is less or equal to the length of R at an intermediate point times B minus A. So you see, instead of equality, we can put inequality, and to replace vectors, I mean vector functions, by the length. So we cannot extend the assertion to vectors, but somehow we can extend it to length of those vectors. Okay, so let us prove it without writing. Just one more remark. Without writing, you don't need. Also, L'Hopital rule cannot be extended, for example, for C, complex numbers. I mean, of course, you cannot divide vectors, right? So for sure, it cannot be extended to more general vectors, right? But even for n equals to 2, for n equals to 2, you may consider vectors as complex numbers, right? And consider vector functions as complex functions. Nevertheless, L'Hopital rule is not valid in general for complex valued functions of a real variable. So one more thing which cannot be generalized. Okay, now let's have a break. Okay, let's continue. Proof. Consider such a function phi of t equals to scalar product r of t times r of b minus r of a. That is, this function phi is continuous on the closed interval and differentiable on open interval. Why? Because the vector function r possess those properties, right? And you see, t is only in one place here, right? No more places. Okay. Now it means apply Lagrange mean value theorem to our function phi. So phi satisfies all suppositions of usual one variable Lagrange mean value theorem. And what it means, so there exists xi in the interval ab such that phi of b minus phi of a equals to phi prime at xi times b minus a. That is Lagrange mean value theorem applied to phi. Now, what is it? Phi of b minus phi of a. Let us write it. Phi of a. That is, if we substitute, so you see, second component of this scalar product is the same for phi of b and phi of a, right? So I can write as r of b minus r of a times the same vector, right? That is why I used just this. So you see, phi of b minus phi of a is scalar product of this vector onto itself. That is the main point. Why I choose phi of t in that form. Now what is it? That is length of this vector squared, right? What is the length of vector in Rn? Square root of a scalar product to itself. So that is length squared. Okay, then what is phi prime? You see, we know how to differentiate scalar product, right? We need to differentiate first times second plus derivative of the second. But the second does not depend on t, right? So it's constant. Derivative of constant is 0. So second term in our derivative of scalar product is absent. Only the first term remains, and we just differentiate. So r prime at xi times r of b minus r of a times number b minus a. Then look, so here we have look at the left hand side. This is non-negative, right? B minus A, of course, is also non-negative. So this scalar product is also non-negative. If it is non-negative, I can put here modulus also, because it's non-negative, in fact. But then apply Cauchy-Bunyakovsky-Schwarz inequality. So modulo of scalar product is less or equal to product of length. So R of xi times R of B minus R of A times B minus A. Now look at the left hand side and at the right hand side. We may cancel that one, right? Of course, we should be careful if it is 0. But if it is 0, then what happens? Look at the very beginning. If it is 0, then this inequality is obvious, right? For arbitrary xi. Because this is inequality, not equality. That's important. So if it is non-zero, then we cancel, right? And we obtain precisely the desired inequality. So theorem is proved. Okay, so now a little bit more about curves once again, and maybe, yeah. So for a moment we considered general vector functions. Now go back to curves. And definition. A curve is called differentiable, continuously differentiable, if R of t, the related vector function, is differentiable continuously differentiable. This is the first time when I give you a definition which is not correct. And I keep it. And why it is not correct? Look, it's the best way to understand what are difficulties here is to remember the interpretation. So vector function, we interpret them as trajectories of a point, right? So imagine we have a trajectory, right? That is our curve gamma, let's say. Right? And in the definition, I said curve is the set of values, right? Now look, if we are looking, look at such a strange movement, for example. You move along that curve, then stop somewhere, go back, and continue. then what happens with such a movement? It gives the same set of values, right? Set of values are the same. So from the point of view of definition of a curve, those two vector functions represent the same curve, but they have different properties. Because when you go back, this can be shown that the function, vector function, is not differentiable at a point. So you see that when you look at a curve as a set of values only, then the related vector function is not defined uniquely. Moreover, properties of that vector function, like differentiability and continuous differentiability, continuously differentiability, depend on that representation, or parametrization as it is called, right? So that definition is not correct from rigorous point of view. And nevertheless, we'll use it. Why? Because usually we accept, so in the following, we admit only such changes of parameter t that give vector functions with the same properties of differentiability. I'll not go deeper in details for a while because also I forget very important property, namely chain rule for vector functions. Yeah. So here we use chain rule. And chain rule for vector functions is like that. So suppose R of t is differentiable, at t naught, t, let's say g of s, is differentiable at s naught, g at s naught equals to t naught, then R of g of s, that is a new vector function of s composition, is differentiable at s naught, and R of g of s prime for s equals to s naught equals to R prime at t naught times g prime at s naught. And in fact, the proof is immediate, because look, we look once again, vector function is differentiable means every component is differentiable, and we apply chain rule for each component. That's all. So you see, there is, let's say, x1 of g of s, so on, xn of g of s prime for s equals to s naught, and we apply chain rule for each of components, and it gives immediately that rule, because g prime is a scalar which can be put, so in fact I wrote it in such an unusual form for linear algebra, because usually in linear algebra we write firstly scalar, then vector, right? But I wrote it in that form because of it's more usual for chain rule, right? To write firstly first map, then second map. Of course, this should be, from the point of view of linear algebra, we should change, right? To write firstly scalar and then vector. And now look, if we look at the definition of, at the chain rule and compare with definition of admissible changes of variable, so you see, if this is differentiable, then after change of variable, we obtain also differentiable vector function. So if we agree to consider only, so if we are looking at differentiable curves, then we accept only changes of variables with differentiable g, right? If continuously differentiable, then g should be also continuously differentiable, and so on. In fact, I didn't introduce, for example, twice differentiability and so on, but of course we can, right? What is twice differentiable vector function? You have a vector, you differentiate it, you obtain once again vector function. If it is differentiable, then it is twice differentiable, and so on, thrice differentiable, so on. So in fact, sometimes we'll need it. Okay, and of course we'll need also to consider smooth curves. But what is smooth? Let me recall what is tangent. Now, so what is tangent? Recall. Tangent line is a limit of chordal lines, roughly speaking, right? So recall, what is tangent line to a graph of a function? If we are looking at tangent at this point, then what we do? We consider chordal line, right? This point is fixed, let's say, m naught. Other point is not fixed. We consider chordal lines, and then we look at limit position, right, of that chordal line as m tends to m naught. You remember this definition of tangent. And by the way, when we discussed limit position of chordal line for function of one variable, it was, I avoid such a notation, right? Instead of that, we considered, if you remember, we consider projections, and we looked at projections only, right? Now we are in more general situation. We are in Rn. R2, R3 doesn't matter, right? But now we have no problem with this, because now we know what means a point tends to another point, right? X tends to x naught, in the sense of several variables. That is no problem. So definition is the same, but now understanding is slightly different. Before, I couldn't write m tends to m naught. Now I can do it. So in first semester, we looked at projections and considered only one variable, right? Now we can consider limit in several variables in the space. And once again, what is tangent line then? Okay, what is chordal? Chordal line. Let's say this is graph of r of t, right? M naught is r of t naught. M is r t naught plus delta t, right? Then chordal line, look, so what is chordal line? Direction of this chordal line is determined by the vector m naught m, right? And this vector is difference of two vectors. So the direction of the chordal line is determined by this equality, right? And okay, of course, direction is not changed if I'll divide by delta t, right? Okay, plus minus. I mean, if you look at vectors, then up to plus or minus. But for lines, of course, it doesn't matter, right? Plus vector or minus vector. Line is the same. Now, for chordal line, it means this vector represents the direction of the chordal line, right? Now, m tends to m naught when delta t tends to 0, right? So tangent line is given, direction of the tangent line is determined by this limit. And that is what? That is precisely derivative. But, so direction of tangent line is determined by this vector. But if this vector is 0, what's about direction? No direction, right? 0 vector has no direction. So it means if we want to consider tangent line, then we need to suppose, so tangent line exists, and that is a proposition. Proposition, which number of proposition? I don't remember. 4? Today? 4? 5. Proposition 5. Ah, yeah, proposition 4 is here, yeah. Proposition 5. Tangent line for a curve gamma given by the vector function r of t is defined if and only if r is differentiable at the corresponding point point t naught, and r prime at t naught is not zero vector, right? So you see that for vector functions to be differentiable is not yet very good because of, so if we want to have tangent, then we need to suppose that derivative is not zero. That is important, right? So we add to the definition maybe as a new definition, and now it is more or less clear why the definition appears. So a curve is called smooth if r of t is differentiable and r of t is not equal to 0. So, of course, this should be supposed at every point of the definition. And also we'll consider piecewise smooth. So, what is smooth? Smooth means that we have a tangent at arbitrary point. So, for example, that is a smooth curve, right? Smooth curve, right? Smooth closed curve. In fact, smooth Jordan curve. But that one is not smooth, right? Because we have points, and in fact, you see, for example, here the function is not differentiable. Why? Because we have different vectors from different sides, right? No derivative. But here we have the same vector, right? But you see that it seems to be the same. But if you look what happens, in fact, look, so you fix a point here, right? And look, if you approach from that side, parameter t is, let's say, increasing from that point to that point. Then here it will be decreasing, right? So signs of delta t are different from different sides, right? But the vector is the same. So it means still is not differentiable, right? Still is not differentiable. Although it seems the same vector. But in fact, we have different limits as delta t tends to 0 plus and 0 minus, and limits are different by the sign. What is the use of that wrong definition when? This definition, yeah, I said it's wrong, but to avoid incorrectness, I added this supposition about changes of variables. So if we agree, if we make extra agreement that we allow only changes of variables such that properties of the functions are preserved, then the definition becomes correct. This we'll avoid those difficulties with like go back and forth. Then it becomes more or less correct. But once again, to make it completely correct, I should give precise definition of classes of parametrizations, to define admissible parametrization, and so on, so on, so on. I don't want to do it, so I make such a, how to say, such a sketch of definition, better to say. So this definition together with agreement, that is a sketch of correct definition, something like that. But you can use it with understanding that what is difficulty behind this. If you say, yeah, so you understand what happens, what may happen, then it's okay. Okay. Then what is next? Yeah. So, for example, what is about possible change of variable for a smooth curve? Now look, if you look at this chain rule, so this derivative should be not zero, right? It means this derivative also should be not zero, right? So change of variable for smooth curve should be differentiable function such that derivative is never zero. For example, x cubed on minus 1, 1 is not suitable as a change of variable for smooth curve, because, yeah, in a point you will get zero derivative, right? And it means, of course, you see, for example, you have a function r of t, right? T in minus 1, 1. Good. Then you make such a change of variable. Once again, x varies from minus 1 to 1, right? So the set of points are the same. But you see, now if you look at derivative of that function, it will be 0 at 0, right? And it means no tangent for x equals to 0. And if that is smooth, then such a problem doesn't appear, right? So this function has a tangent, right? At t equals to 0, if we suppose r is smooth. But when you make such a change of variable, then you cannot define tangent line at x equals to 0, right? Although we know it exists because we suppose this function is smooth, right? And it means we should exclude this possibility to change variable for smooth curves. But if we are looking only at differentiable, then no problem, right? For differentiable, it's no problem. Okay. So, oh, I have 5 minutes. I can make a definition. In fact, it was given, but it was given with different words. Now I'll give it, but that is the same, in fact. So, definition. Vector function r of t, t in AB, has a bounded variation on AB if the supremum of such sums is finite, where the supremum is taken over all partitions P, let's say A equals to T naught less T1 less Tm equals to B of AB. This supremum is called total variation of R on AB, and notation is V of R. Also, if we want to indicate the interval, then we add the interval. Total variation. And look, what is geometrically? So remember, we have a vector function, right? That is R of A, this is R of B. So somewhere we have line T, A, B, right? So A corresponds to that point, B corresponds to the terminal point, right? And then we consider a partition, right? Like moments of time. So we indicate some moments of time, right? Then look at our curve at those moments. So these are some points, right? These are some points on our curve. So that is R of T m minus 1, here R of T1, and so on. And then what are those modulus? Length of this interval, right? Straight intervals of straight lines which connects those points, right? So what is written here is the length of this rectangular curve, right? And now we consider supremum of all such sums. We know that is length, right? It was defined as the length. So, in fact, remark. Curve is rectifiable if and only if the related vector function has bounded variation. The total variation is called the length of the curve. So you see that we considered this notation before, in fact, but with different name. The definition of chain rule. What means definition of chain rule? Chain rule is this one. That is chain rule. What is definition of chain rule? Strange question. Okay. That's all for today. Thanks for your attention.